So section 3.6 deals with modeling exponential and logarithmic functions. So in the last section, we were looking at a very specific application, and that was financial data. You would either have it compounded a certain number of times a year, or we would compound continuously, and we would use E. Now we have to decide sometimes whether what we're modeling is logarithmic or exponential and use the form, or appropriate form. So number 17 says, Jennifer is terrified of spiders. Much to her horror, she finds a spider nest in her basement and lays down some poison traps. The population of spiders is supposed to decrease exponentially if the poison works properly. If it takes 12 hours for the first 10% of spiders to die, then how long until 75% of the spiders are gone? Round your answer to the nearest hour. So because it says we're decreasing exponentially, we assume in these types of models that we're dealing with continuous. And that actually makes sense. If you lay down poison, right, once the process starts, the poison doesn't just switch on and switch off like, like quarterly interest does, right, or monthly interest. You only take it at those intervals. The poison's there the whole time. So this is a continuous process once it gets started. So the model that we want to use is the population of spiders should be whatever the initial population is, right? E to the RT. We know our rate should come out to be negative because we're decreasing exponentially. So one of the other things you've got to keep in mind here is P in this equation is telling you what you have left. So notice in here we were giving you percentages of the population, and we actually didn't say explicitly how many spiders we had. So make sure to read this very carefully, because students tend to sometimes invert the numbers and not read what's going on. So the first set of numbers we were given is it said that 12 hours later, 10% of the spiders died. That doesn't mean you're down to 10% of the population. This means if 10% went away, there's still 90% of them left. And we want to know how long is it until 75% are gone. So really what that's asking is how long until there's only 25% left. Now, if I had said it took 12 hours for there to be, or at 12 hours later we were down to 10%, right, then we would use 0.1. So keep in mind, if we give you the information in terms of what has disappeared, you have to subtract that from 100 to figure out what's actually left. And one of the ways I explain to my students is think about this when you go shopping and you see sale prices. They never advertise a sale by what you're paying. They always give you the percentage that you're saving. So if there's a 20% off sale, you're paying 80% of the price. So this formula wants to know what's actually there. So we're going to use the first piece of information, which says that when T is 12 hours, P is 0.9, right, times what you started. You have 90% of the spiders left. So 0.9 times P naught equals P naught E to the 12R. And what we need to do is we need to find the rate of decay. So the initial amount's going to cancel, and then I can say 0.9 equals E to the 12R. We can take the natural log of both sides. So the natural log of 0.9 divided by 12 is the rate of decay. Now this rate should be negative, and this rate actually is negative because the natural log of numbers less than 1 are actually negative values. So this is actually a negative divided by a positive. Now we want to know, well, how long until there are 75% of the spiders are gone? So that means we want to find at what value T is P equal to 0.25 P naught. So one of the cool ways you can do this, because these can get really messy, one of the ways you can kind of make your algebra a lot cleaner is you can say, well, I'm just going to set up the equation And even though I have the rate, I'm not going to plug it in yet because this is kind of nasty to write all of that mess up inside of here. So I'm going to set it up like this, and we can see the first step is to cancel P0. Then we take the natural log of both sides. So nothing says I have to plug in all the numbers I have at one time. Sometimes it's a little bit better to do the algebra with the variables and then plug the numbers in when it's convenient. So now that I'm here, now this is a better place to plug in my rate. And now it's much easier for me to solve for t. So I can see I multiply both sides by 12 and divide both sides by 0.9. And just like we did in the previous problems, you want to do all of the algebra steps, and then we're going to adjust it and round to the nearest hour. All right, now another thing to keep in mind when we talked about those log properties, we said, well, if you have log of two things being divided, right, you can split them up. Well, this is different. You cannot combine these into the same log because it's log of something over log of something, right? So this has to be put in as is. So I'm going to show you in the calculator how to correctly type this in. So we have 12, right, times natural log of 0.25, close your parentheses, divide natural log of 0.9, and then close your parentheses. And so we get 157.89 hours. And we were told to round to the nearest hour, so that is going to be 158 hours.